All right, so in this lesson, we're going to have a look at what happens with energy. So we'll call this energy in SHM and damping due to friction. Okay, so in our simulation, what we've looked at up to now is what happens when there's no friction. That's not a really realistic situation. So what we'll have a look at now is the energy transformations in SHM, and they're fairly straightforward if we start thinking about what's going on with energy, but also energy losses and their effect on SHM. Okay, so firstly we'll have a quick look at what's going on with energy. So we'll have a look at this pendulum here, and on the left hand side of the screen you can see a kind of bar graph. And what you can see, if I raise this pendulum up to one side here, that the potential energy is increasing. So I'm actually going to leave it there and pause it and lift it up to its starting position. Oops, I'll go to there. So you can see that at this starting position, because we've now lifted it up from its equilibrium position, it has a lot of potential energy, but it's not moving, so it has no kinetic energy. If I hit play here, you can see that it loses its, in fact I'll change it to slow motion. You can see that as it swings out to its maximum position, it loses its kinetic energy and it's all potential. As it swings back through equilibrium and gains speed, it loses all of its potential energy and it becomes kinetic. Throughout the motion, however, the total energy of the system remains constant because energy is conserved. Okay, so energy gets changed back and forth at the extreme positions. So with big displacement we have lots of potential energy, and as it swings through equilibrium it's lost all the potential energy and it's gained the kinetic energy. Alright, so let's summarize that. So during simple harmonic motion, energy changes back and forth between potential energy and kinetic energy. We can say at max displacement, all energy is potential, and at equilibrium all energy is kinetic. And we can say, note that total energy remains constant. Okay, so what we looked at is what's going on in the absence of friction. So what we'll do now is we'll just add to that the concept of damping. Damping is when SHM loses energy due to friction. So we call that process damping. That's a term we need to be familiar with. Alright, so if we look at this same oscillator here, if I turn friction up here, we can see that now during each swing, as it swings through the air, it's colliding with air particles, and that's kind of slowing it down. That means that with each swing, it won't get quite as high because it's now lost some energy during each swing, and during the motion more and more energy is converted to thermal energy or heat energy of the air particles that it's smashing into. And so we see that the motion kind of winds down gradually, and a bit of energy is lost in each cycle, converted to thermal energy. However, as it slows down, it's moving more slowly, so with each oscillation it's losing a little bit less energy because it's not moving quite so quickly through the air anymore. And so the process of damping, we're going to lose energy gradually, but the rate at which we're losing energy is going to decrease with each cycle. And eventually, if I let this swing at a normal speed, we can see that the motion really winds down. It becomes smaller and smaller, and more of its energy has been converted to thermal energy, and that's kind of been lost from the system. We can't get that back. And eventually the oscillations become very, very small, and it kind of peters out, but it takes a long time to stop. Okay, so that's damping, and we're just going to have a look and see what that looks like on a graph. So we can say that during damping, the period remains constant, but the amplitude decreases as the system loses energy. Alright, so what we'll do is we'll have a look and see what the displacement time graph looks like for this motion. So this is something you're going to need to be able to reproduce. So we got, I'll do one more step here. So this is x in meters. This is that's the displacement. And then we'll look at, so it's that 1, 2, 3, 4. And then we'll go 1, 2, 3, 4. So we'll look at 3 cycles, and then we'll go 1, 2, 3, 4. So this is going to be a period, and then 1, 2, 3, 4. This is going to be 2 periods, and this is going to be 3 periods. So we'll have a look and see what happens to this amplitude over 3 periods. So in our first period, we have a big amplitude, but the amplitude is going to decrease gradually. So it's going to get smaller and smaller. So now it's going to be a little bit less. In fact, I'm just going to draw a little curve to help me, and I'll explain what this curve is. In fact, I'll just erase these points that I've done. I'm going to draw a little curve just to guide how I'm doing this. The amplitude is actually going to decrease exponentially here, like this. So we call this line here, this is the exponential envelope, and the amplitude is going to decrease exponentially. So what we can do is draw our points as we would, but now the amplitude is getting smaller and smaller in accordance with this exponential envelope here. Okay, so we then have our normal displacement time graph, but with a decreasing amplitude. And it's going to continue to get flatter. So my curve here is slightly misleading in that it seems to completely flatten out. It is flattening out, but it is still decreasing, just at a slower and slower rate. Okay, so the key here is that this is the starting amplitude here, and it gets smaller and smaller. So this is the amplitude at start. But the amplitude of the oscillations gets smaller and smaller and smaller. This is a kind of tricky graph to draw, but if you draw in the envelope first, and then if it doesn't look like you've quite drawn it to look like a good exponential, then just make sure you label it to say that it's an exponential envelope. And as the oscillations lose energy, the envelope gets a little bit, the amplitude gets smaller and smaller because it's going to have a little bit less potential energy at each end, which means it's not going to get quite as far out. So that's basically what we need to know about damping, and that's the effect of friction on a simple harmonic oscillator. Okay, so just to summarize, energy changes back and forth. This is a summary. Between potential energy, which is max at max displacement, and kinetic energy, which is max at x equals 0, and damping causes energy loss. It's actually converted to heat, which results in exponential decay of the amplitude of the motion. Okay, so that's energy and damping. In the next presentation, I will go over resonance, which is a way of restoring some of the energy to the system.